Hello, freshmen. Welcome to our post-laboratory discussion in Module 3 of MTChem 1 Laboratory. For this discussion, we will be discussing our results and observations for the two experiments that we did at home, which are the types of chemical reactions and solutions. I am Ms. Angela Joy Lozano, your module writer for Module 3. Before we start with the discussion, let's take a look at our objectives for the experiment. For the two experiments, you are expected to differentiate the different types of chemical reactions and observe the changes that occur among them. And you're also expected to be familiar with the properties of solution and the factors affecting solubility. Hopefully, as we go through our post-laboratory discussion, you will be able to see if your observations and results are correct. Let's start with the first part of our post-laboratory discussion, which is the chemical reaction. For this one, we have 4 setups that you did. Let's start with the first one, which is setup A, wherein you are required to combine vinegar and baking soda together in a clear glass or clear bottle to observe this chemical reaction. What is this evidence of chemical change that we are referring to? For setup A, you are expected to observe bubbles, which indicates the formation of gas. This formation of gas indicates that there is gas produced and there is gas included in your product. So upon combining the vinegar and baking soda together, there is the production of gas. And this is observed through the existence or the formation of bubbles. Let us take a look at the chemical equation of this experiment that you did. For setup A, the chemical equation is, we have here the sodium bicarbonate combined with acetic acid will produce sodium acetate, water, and carbon dioxide. For your reactants, we have the sodium bicarbonate, which is found in your baking soda, and we have the acetic acid, which is found in the vinegar. Combining these two reactants will produce the sodium acetate, water, and the carbon dioxide. And this carbon dioxide is the gas that we observe in this formation of bubbles. As you can see in these given pictures, the bubbles can be seen much clearer, indicating that there is a production of gas. Let's now proceed with the chemical reaction that occurred in this setup. For this setup, we have two types of reactions, which is the double displacement reaction and the decomposition reaction. For the double displacement or double replacement reaction, we have here the sodium bicarbonate combined with the acetic acid will produce sodium acetate and carbonic acid. We have to remember in the double displacement reaction that there is partner switching. Again, for our reactants, we have the sodium bicarbonate found in the baking soda and the acetic acid found in the vinegar. For the first product, we have here the sodium in the sodium bicarbonate will combine with the acetate in the acetic acid, producing sodium acetate. For our next product, we have the remaining hydrogen for the acetic acid will combine with the bicarbonate in the baking soda to produce carbonic acid. Again, you can observe the partner switching between the two reactants to produce our products. Now, for the decomposition reaction, we have to put in mind that carbonic acid is an unstable compound, indicating that it can immediately and can easily undergo a type of reaction. For this instance, we have the decomposition reaction. So carbonic acid will undergo decomposition reaction to produce water and carbon dioxide. Right? So from this diagram, you can observe the two different types of reaction that occurred in our setup A. Thus, our final product in this one is sodium acetate and water and carbon dioxide. Okay? Again, carbonic acid is not a final product because it is unstable and will still undergo decomposition. So these three are our final product. Let's now proceed with the setup B, wherein you are expected to combine sugar solution and yeast together. For this experiment, your materials are sugar, hot water, yeast, and a clear glass for you to be able to easily observe the chemical reaction. So for this setup, what are the evidences of chemical change that you need to look out for? You need to look out for bubbles, which indicates the formation of gas. For this picture that is shown, you cannot clearly see the bubbles that are forming because this is in the early stages of the experiment. So if you did it at home, it should look like the second picture, wherein a lot of bubbles are already produced. As you can see, there is a formation of bubbles in this one, indicating that gas was produced in our experiment. Now, what is the type of chemical reaction that occurred between the yeast and the sugar solution? We have here fermentation. Fermentation is when sugar is converted into alcohol or acid and a gas. For the chemical equation that we are to use for setup B, we have this one. So we have here your table sugar plus your hot water and yeast will produce ethanol and carbon dioxide, which is in form of gas and can be observed through the bubbles. So how does fermentation happen in this setup? You have to remember that yeast is a microorganism. Okay, it will be using the table sugar to produce and synthesize ethanol and carbon dioxide. Just remember when there is someone baking and they will set aside the dough first because they use yeast, they allow the dough to rise. Okay, because yeast is synthesizing the sugar in the dough to produce carbon dioxide, making the dough rise. Let's proceed with setup C. For setup C, you are expected to combine hydrogen peroxide, or what we also know as agua oxinada, and yeast. So we have, again, agua oxinada, dry yeast, and a clear glass to observe this kind of reaction. For this setup, what is the evidences of chemical change that you are ought to observe? Again, it's bubbles indicating the formation of gas. As you can see in this picture, there is a distinct amount of bubbles observable in this setup. Okay. If you also observe, there is also an increase in temperature in your container. So what is the chemical reaction that occurred in this one? The type of reaction that occurred in this one is simply decomposition, wherein, shown in our chemical equation here, we have the hydrogen peroxide combined with yeast, which is a microorganism, will produce water and oxygen, wherein oxygen is in the form of gas and can be observed in the existence of bubbles. Setup C, or decomposition reaction, is the concept behind the catalase test. Catalase test is used to detect the enzyme catalase in a microorganism, and it is used to differentiate the catalase positive from catalase negative organisms. When we say catalase positive, it means it has catalase in them, and of course catalase negative, meaning catalase is not synthesized by this organism. Let's take a look at this video and see how do they use setup C, or the catalase test, to observe the existence of this enzyme. First, we will be preparing the glass slide, okay? And then you will be using hydrogen peroxide, just like what we used in our setup C. You just need to put a droplet of the hydrogen peroxide. Again, this will serve as an indicator if the organism produces catalase or not. Using a wooden stick, you will get a colony or a sample of microorganism from the milieu. And then you will simply introduce it to the droplet of hydrogen peroxide. And then if you can observe, this white particle indicates that there is a production of gas because there is a formation of bubbles. The production of gas indicates that the microorganism tested is positive to the enzyme catalase. Okay? Again, you simply need to observe if there is a formation of gas upon adding hydrogen peroxide. Let's now proceed with the last setup, which is setup D, or heating of the spoon. For this setup, the materials that you needed were candle, a match, and a spoon to observe this type of reaction. So what is the evidences of chemical change observed in this setup? First, there is a formation of the black soot or the black part in our spoon. There is also an existence of the black smoke once you introduce the spoon to the flame in the candle. So what is the type of reaction that occurred in this one? For setup D, the type of reaction is what we call combustion. For this reaction, we have two types. We have the complete combustion and the incomplete combustion. Let's take a look at their chemical equation. For complete combustion, you have the paraffin or the C18H38 combined with oxygen will produce carbon dioxide and water. As simple as that. Incomplete combustion, on the other hand, is paraffin combined with oxygen will produce carbon monoxide, and hydrogen. Now, what is the difference between the two aside from their products? Let's take a look at this table. For complete combustion, it involves complete burning of fuel. This occurs when there is enough oxygen present in your environment. Okay? The flame that is produced is also in the color blue. This is what we also call as a true flame. And their products, of course, is carbon dioxide and water. Again, in complete combustion, it's complete burning of the fuel. There should also be enough oxygen present in your environment. Incomplete combustion, on the other hand, involves partial burning of the fuel. This partial burning is because there is not enough oxygen present in your environment. Okay? The flame that it produces is red orange. This is observed that, say for example, when you light up the candle, it produces an red orange flame. The products are carbon monoxide, carbon which is in the presence of the black soot, and the water. Okay, so with the heating of the spoon, the reaction that we observe there specifically is incomplete combustion because there is the production of the black soot or the carbon. Let us now proceed with the second part of your experiment, which is solutions. For the solutions, you have here again 4 setups. Let's start with the solubility of solids. When we discussed with your pre-laboratory discussion with the solubility of solids, we will be using the terms soluble and insoluble. For the first setup or the setup A, you are tasked to combine salt with different solvent, which is water, alcohol, and acetone. Start first with water. You have to remember that the chemical equation for salt is NaCl, wherein sodium is positive and chlorine is negative. Water, on the other hand, has both the charges positive and negative. So how is salt soluble in water? Since sodium is positive charge, it will interact with the negative charge in the water, as well as the chlorine. The negative charge of the chlorine will interact with the positive charge of the water, making it soluble. We also have to remember that we are following the concept of like dissolves like. So since water is considered as a polar solvent and it is combined with a polar ionic solute, which is your salt, it will be soluble. And then as you can see in this one, right, there is minimal salt granules, but most of them dissolve. Maybe upon a bit of stirring, it will be further dissolved. Let's proceed with the next solvent, which is the alcohol. Salt is insoluble in alcohol. Why is that? Alcohol is considered as a semi-polar. Yes, alcohol is a polar solvent, but it is a semi. What does it mean? It means that there is less charge in them, okay, making it harder for the charges to interact with the charges in our salt, making it insoluble. The same concept applies when you combine acetone and salt together. Salt combined with acetone is insoluble because acetone is a weak polar. There are lesser charges in them, making it difficult to interact with the charges of our salt. And then as you can observe, ethanol or alcohol, you can observe the salt granules that are not dissolved, indicating that salt is insoluble in both alcohol and acetone. Let's take a look at the polarity index and the boiling point of our solvents. We have here acetone with polarity index 5.1, ethanol with the polarity index 5.2, and water with the polarity index 10.2. What is polarity index? Polarity index is how much polar and how much charges does the solvent contain. So as you can see here, acetone and ethanol have very weak polarity index, indicating that it cannot dissolve, okay? It has very little charges and cannot dissolve salt in them. Unlike water, which has a high polarity index, indicating that it can dissolve polar ionic solutes. And then we also have here the boiling point. As you can observe again, the lower the polarity index, the lower the boiling point is. Let's now proceed with our setup B, wherein using the same solvent, which is water, alcohol, and acetone, we will try to dissolve a new solute, which is tawas. Tawas is a polar ionic similar to our salt, so it will now produce the same result as our first setup. So upon combining water and tawas together, tawas will be soluble in water. It will also be insoluble in our alcohol, as you can see here. They settled at the bottom, and it will be insoluble again in acetone. Again, this is because alcohol is a semipolar containing few charges, similar with acetone, which has also few charges that can interact with the charges in the tawas, making it insoluble. Chemical name for tawas is aluminum potassium sulfate, or it is also called as potash alum. Chemical formula is KAl, or aluminum, and then we have this here, the sulfate. Let's now proceed with the discussion of polar solvents and non-polar solvents. So first is the definition. Polar solvents are liquids that have large dipole moments, while non-polar solvents are liquids that have no dipole moments. Now, what is this dipole moment that we are referring to? Let me give you an example. Let me first draw the Lewis structure for water, or for H2O. We have here oxygen is bonded with 2 hydrogen. When we say dipole moments, this is represented and looks like an arrow, wherein it starts with the positively charged element and then it points towards the negatively charged element. For this example, for the H2O, we have positively charged hydrogen and then the negatively charged, which is oxygen. So if we are going to go back to the definition of dipole a while ago, we have an arrow wherein it starts with a positively charged element, which is the hydrogen, and it points towards the negative charge, which is the oxygen. Now, for us to identify if it is dipole or no dipole, both arrows, okay, need to point towards the same direction. And as you can see in this one, they are both pointing towards the negative charge, which is in the oxygen. This is now polar, okay, because it has a large dipole moment. Let's take a look at if it's in the carbon dioxide. Carbon dioxide, its Lewis structure will be like this. Again, in dipole moments, we have here the positive and negative charge. The positively charge will be pointing towards the negative charge. So the negative charge here are the oxygen, and the positive charge is the carbon. So starting from the positive, will be pointing towards the negative. So they are both pointing in the opposite way. Unlike the H2O, wherein they are both pointing at the same way, which is towards the single negative charge, this one now has no dipole because they are both pointing the opposite direction, canceling these two arrows, meaning our carbon dioxide now is non-polar. Next is the ability to dissolve compounds. Polar solvents can only dissolve polar compounds, and then non-polar solvents can only dissolve non-polar compounds. Again, in this one, we are following the concepts of like dissolves like. Then we also have the charge separation. Polar solvents have a partial positive charges and partial negative charges that can be observed. Non-polar solvents, on the other hand, have no charge separation. For electronegativity, in polar solvents, molecules contain atoms with higher differences in electronegativity. Atoms in the molecules in nonpolar solvents have nearly similar electronegativity values. Say, for example, in water, you have to remember that the electronegativity of polar solvent should be greater than or equal to 0.5. Let's take a look at water. Hydrogen has an electronegativity of 2.1, while oxygen has an electronegativity of 3.5. We just need to subtract both of them, so we will be getting 1.4, and 1.4 is greater than 0.5, indicating that water is a polar solvent. Let us now proceed with the next part of our solutions experiment, wherein for this part, we will be observing the solubility of liquids. Kindly remember that in talking about solubility of liquids, we are to use the terms miscible and immiscible. For this one, kindly take a look at this picture. These are the pictures of the results upon combining the different solvents with each other. So first we have water and ethanol or alcohol. We also have water and acetone. And then finally water and oil. And then here are their miscibility with each other. We'll start first with water and ethanol, which is this middle test tube. And then as you can see, it's miscible, meaning you cannot identify anymore which is the ethanol and which is the water. So why is it miscible? Remember that rule that we are following in solubility of compounds, like dissolves like. Since water is a polar solvent and ethanol or alcohol is also a polar solvent, then they tend to dissolve each other. So it's miscible. Another thing is that ethanol has the functional group, which is the OH or hydroxyl group. This hydroxyl group is considered as a hydrophilic group, which means it's water loving. Okay? This results in the hydroxyl group attaching to water with a hydrogen bond, causing them to dissolve with each other. Thus, their solubility with each other is miscible. Next, let's proceed with water and acetone. Similar with the first one, they are also miscible with each other because they are both polar solvents. For the last one, we have water and oil. And then as you can see in our miscibility, they are immiscible with each other. Just take a look at our picture. We have here the oil and you have your water. You can easily distinguish them with each other, indicating that they did not dissolve or mix with each other. So why did it happen? Remember that water is a polar solvent and oil, okay, is a non-polar solvent. An oil contains what we call the hydrophobic molecules. When we say hydrophobic, this means water fearing. Natatakot sila sa tubig. They fear water. Okay? And because of this, instead of mixing with water, they repel it. They repel it, causing them to not mix with each other. So oil, okay, being hydrophobic is the opposite of our OH group, which is hydrophilic. This causes them to not mix, making water and oil immiscible with each other. For the next part and the last part of our experiments, again, we have different solvents that we are to mix with each other and we are to observe their miscibility. We have here ethanol, acetone, and oil. So for the first one, we have ethanol and acetone. Both of these solvents are polar. Again, if we are to follow the rule, which is like dissolves like, since both of these are polar, they are miscible with each other. Then as you can see in this test tube A, you can see that you cannot identify which is ethanol and which is acetone. Next one, we are to combine ethanol and oil with each other. Ethanol is a non-polar solvent and oil is a non-polar solvent. Okay, so we have different polarities between our two solvents, causing them to be immiscible. We have here the ethanol, and then you also have the oil at the bottom. Okay? Just by looking at it, you can identify that they do not mix with each other. And then last one, we have the acetone and oil. They are again immiscible with each other because acetone is a polar solvent while oil again is a non-polar solvent. They are different in terms of polarity, causing them to not mix with each other. So we have here the oil and the acetone. Okay, you just have to remember that like dissolves like. That is the concept that we always follow in terms of talking about solubility of solutions. Let's take a final look of our results. Again, we have water and acetone. This is miscible. Water and ethanol, this is again miscible. Water and oil is immiscible. Ethanol and acetone is miscible. Ethanol and oil is immiscible, and acetone and oil is immiscible. Okay? Mostly these immiscible ones, they contain oil, which is a non-polar solvent. Let's now proceed with the problem solving that are included in your laboratory worksheet. You are given one problem, but there are various questions that follows them. First, read this one. Mark and Johnny are two medical technologists working in a district hospital. They were asked to prepare the following solutions in the laboratory. Mark prepares 2.5 grams of sodium hydroxide pellets dissolved in a 750 ml of solution, while Johnny was asked to prepare 2 liters of 0.01 moles solution of hydrochloric acid. For your final answer, show the complete solution per item, and then your final answers should be rounded off to two significant figures, which the process of rounding off and using the significant figures are discussed during your lecture. So for our first question, we have here, calculate the molar concentration of the NaOH solution that Mark has prepared. So we are to look for the molar concentration of our given. In looking for molar concentration, we are to use M is equals to mole of the given divided by the liters. Okay, let's now identify first what are the given. Okay, since we are only talking about the sodium hydroxide solution that Mark has prepared, so our given here is 25.5 grams of sodium hydroxide, 25.5 grams of NaOH, and the 750 ml. As you can see, none of our given follows the unit of measurement that should be used in our formula. So we are to convert all of these quantities first. Let's start with our liters first. So you have here 750 ml. You have to convert it to liters by simply dividing it by 1,000. Okay, because 1 liter is equals to 1,000 ml. And this is 0.75 liters. Okay, so we have now 0.75 liters. Now let's proceed with converting these grams to moles. And in converting grams to moles, we have to look for our molar mass. Okay. And in looking for the molar mass, we have to look for the atomic weight or atomic mass of each element in our compound. So we have here N, A, O, and H. Let's take a look at our periodic table. So for sodium, we have 22.99. And then for oxygen, we have 16.00. And then for hydrogen, we have 1.008. All you need to do is add all of this together and you'll be getting 39.998 grams per mole. Now that you have your molar mass, you can now proceed with converting grams to moles by simply multiplying it by 1 mole of NaOH or sodium hydroxide over our molar mass, which is 39.998 grams of NaOH. Then you simply cancel out the same units, and then you will be getting the answer of 0.637531876 moles of NaOH. And then using this number, you can now proceed with our molar concentration. Okay? You can now proceed with solving for the molar equation, wherein molar concentration is equals to moles, which is our 0.637531876 moles of NaOH. You divide it by our liters, which is 0.75 liters. Then our final answer, which is again rounded off to two significant figures, our final answer would be 0.85 moles per liter of NaOH. Okay? Hopefully you got it. Again, just a quick run over of what we did. First, we identified what is the missing, okay, which is molar concentration. From this, we extracted the formula to be used, which is molar concentration is equals to moles divided by liter. And then we identified the given to use. So this problem only asks for the sodium hydroxide solution that Mark has prepared, wherein it's 25.5 grams of sodium hydroxide dissolved in 750 ml of solution. And then you can double check the units of measurement. For the first one, we have grams. And then for the second one, we have ml, which does not follow the formula to use. So what you're going to do is you're going to convert it. Starting first with our ml, simply dividing it by 1,000, and then you're going to get 75 liters. And then you proceed with converting these grams to moles. To convert it from grams to moles, you need to get molar mass. Again, in getting molar mass, you simply need to get the atomic weight or the atomic mass of each element in our compound. That is the sodium, oxygen, and hydrogen. Simply add them all together. And then you can proceed with solving for moles, wherein you multiply your given, which is 25.5 grams, times 1 mole over your molar mass. Okay, and then you will be getting your moles. Upon getting your moles, you can now solve for your molar concentration. All you need to do is you divide your moles to your given liters, and then we will be getting our final answer, which is 0.85 moles per liter of sodium hydroxide. Hopefully you get this one. Let's now proceed with our next question. For our next question, we need to calculate the moles of HCl needed by Johnny. We're still on the question or the problem from the first one. Okay, so for this one, we are only talking about the hydrochloric acid needed by Johnny. So let's identify the given. So for this one, we have 2 liters of the 0.01 moles of solution. That's 0.01 moles of solution of HCl. Kindly remember and keep it in mind that this capital M stands for molar concentration. Okay, so if we are talking about molar concentration, we will use the formula for molar concentration, which is also the same from the solution or formula that we used a while ago. That is M is equals to moles divided by liters. But the difference for this one is that we are looking for our moles. So what we're going to do now is to simply substitute the given values. So we have our molarity or molar concentration, which is 0.01 moles, is equals to moles, which is what is missing, divided by liters. And then our given liters is 2.00 liters. Okay? And then what you need to do here is you simply need to cross multiply. Okay, so in cross multiplying, you will come to the equation 0.01 moles or molarity is multiplied by 2.00 liters is equals to moles. Okay, now you simply need to multiply them to arrive at our final answer, which is moles is equals to 0.02 moles of HCl or hydrochloric acid. This is now our final answer. Okay, you might be asking where is the unit of measurement moles from. Remember that capital M can also be written. M is also the same as mole per liter. Okay, so if you were to write it here, change this one. If you were to write mole per liter, okay, liters will be cancelled, mole will be retained. So that's where our unit of measurement for moles came from. For our last problem, we have here, if Johnny has 2 liters of 0.01 molarity of hydrochloric solution, what would be the final concentration if he dilutes it further to 3.5 liters? So in this one, we're talking about dilution and we're looking for our final concentration. Remember that in looking for dilution, we are using this formula wherein C1V1 is equals to C2V2. Let's now analyze the problem and identify first our given. We have to identify which is the first concentration, the volume, the final concentration, and the final volume. So for the first concentration, we have here our 0.01 moles or molarity of HCl. For its volume, we have 2.00 liters. And then we are looking for our final concentration. So let's mark it as X. And then our final volume is 3.5 liters. Okay? And then all you need to do is substitute this given to our given formula. So we have the concentration 1, which is the 0.01 moles. Multiply it by our volume, which is 2 liters. This is equals to our missing, which is X, multiplied by 3.5 liters. Now, what you need to do here is first multiply this 2. So it would be 0.02 moles is equals to X times 3.5 liters. Then all you need to do for our final step is to divide both sides by 3.5 liters. Okay, so you need to divide it by 3.5 liters, divide it 2 by 3.5 liters. When you cancel this out, you'll be remaining with X. That's equals to, divide this and you will be getting the value, which is 0.0057 moles per liter of HCl. Okay? Remember that we are to round it off in two significant figures. Although this is already into significant figures because leading zeros are not counted, let's try to transform it into a scientific notation. So if we are to transform it to a scientific notation, we will move the decimal point 1, 2, 3 times to the right. Okay, which will give us the scientific notation of 5.7 times 10 raised to negative 3 moles of HCl. This is now our final answer. Okay, actually both of this can be our final answer, whichever you prefer. We're now done discussing our post-laboratory. So we've already discussed about the results of the different types of chemical reactions. We've also discussed the solubility and solutions. We've also discussed the different problems, okay, included in our problem solving. So if you have any questions about our post-laboratory, please don't be shy to email me at my email or to message me in Canvas. Thank you and God bless.